We've been talking about these intermolecular forces, but we didn't really say what they are. So now we're going to talk about exactly what they are. So these are forces of attraction between molecules. Inter means between. Intra means within. So an intramolecular force is within a molecule. Intermolecular means between. So we've heard of intercollegiate sports as opposed to intramural sports. Intramural sports, the college has a bunch of different baseball teams that play each other. People sign up for intramurals, and you're playing teams made of students from your same school. Intercollegiate means that your college's team plays the team from a different college. It's between colleges. So intermolecular, these are forces between molecules. And the strength of those forces affects whether it's a solid, a liquid, or a gas at room temperature. The nature of these forces is electrostatic. Electrostatic is the attractions between opposite charges. If we've got strong intermolecular forces, we're going to have liquids and solids at room temperature. Weak intermolecular forces will result in gases at room temperature. So what are these forces? Well, the first one we're going to talk about is a dispersion force. This one goes by a lot of different names. It's also called the London force. I have a name I prefer. I prefer induced dipole force. It's also called van der Waals force. Like, could we just agree on one name? But this is the force that is present in everything. This force is caused by fluctuations in the electron distribution within the molecules or atoms. All molecules, all atoms have electrons. Electrons can have these fluctuations, so everything has dispersion forces. So if we look at a helium atom, so here's a helium atom. Helium atom has 2 electrons. So here's the nucleus, and it has 2 electrons. Those electrons are doing their kind of randomy electron things. We've talked about electrons and how squirrely and unpredictable they are, right? They're not traveling in nice little circular orbits around the nucleus. They're in these orbital distribution of probability areas. So if we looked at the electron position at one time and another time and a third time, we would see that sometimes the electrons are on the same side of the atom. I have 6 children. I still say that sometimes just to shock myself. When they are all home, they are usually fairly randomly distributed about the house, right? But I remember one time in particular, all 6 of them were sitting on the couch. I think one was reading a story and the others just crowded around. And I actually took a picture of it because it was such an unusual thing. I mean, 6 of them all on the one couch, and they weren't even spread out. They were all on one end of the couch. I'm like, how do you guys even fit there? I mean, I understand them all coming to the table for dinner when that happens, but just random, right? Stuff like this can happen. So the electrons could all randomly be sitting on the couch together. This causes an imbalance in the distribution of charge. We have positive charge at the nucleus, and the electrons are the negative charge. When the electrons are on one side, that makes this side of the atom a little more negative than the other side. This funny looking letter here is a lowercase Greek delta, and we use that to stand for a partial negative charge. This is not an ion. An ion would have a -1 or a +1 charge or +2 or something. This is a fraction of a charge. So maybe 1/3 of a charge or 1/10 of a charge, but a little bit. And then there's an equal but opposite positive charge on the other side. Well, if this happens in one atom, we've got a negative here and a little bit of a positive here. This positive is going to attract the electrons in a helium atom that's nearby. And it's going to induce a similar situation in the next one. This one, having a negative here and a positive here, this positive is going to attract the electrons of another one. And we've got this weak attraction between this partial positive and partial negative charge. These are called dipoles. So the Earth has a north pole and a south pole, right? And those are magnetic poles, and that's why a compass works, because it'll line up along these electric fields that go through the north and the south poles. So it's a two-pole, and the opposite ends are different. So this is the helium atom having a dipole. It's an instantaneous dipole. It happens randomly, and it doesn't last very long. All 6 kids did not stay on that one couch for 3 hours. It was maybe 5 minutes, right? It was just like so brief. And then it's gone. So we'll get a dipole just spontaneously happening here, which induces a dipole in the neighboring atom. And there's this attraction here. And then these electrons go back to what they were doing, and then those go back to what they're doing, and it's gone. So these dispersion forces are very brief, and they're very weak, but they're also very frequent. And so they do add up. Any questions yet? So the dispersion force is the instantaneous dipole in one, inducing a dipole in the other, and then they're being attracted. Now, how strong that force is depends on how easily those electrons are shifted. In an atom like helium that only has 2 electrons, those electrons are very close to the nucleus. They don't shift around that much. There's just really not even that much volume for them to shift around in. Turns out that as the atom gets larger and larger and larger, it's easier to shift that electron cloud around. You can kind of think of something getting larger and larger. It gets kind of flabby, maybe, like a big bowl of Jell-O or something, and it's easier to squish around. So a larger electron cloud, more easily polarized. So size generally increases with molar mass. So we can use molar mass as a guideline, but only when we're comparing similar things. If we're comparing, say, noble gas atoms, or we're comparing hydrocarbons, something similar, we can use the molar mass. But you can't take the molar mass and use it to, compare xenon with a water molecule. And it's like comparing apples and oranges. It doesn't work. So here are the noble gases. These are all in the same family, so we can compare them. And here are their molar masses. Helium is the smallest, xenon is the largest. And so helium, neon, argon, krypton, xenon, we're increasing the size of the atom. Larger atom, easier to polarize. Look what happens to the boiling point. These boiling points are really low because the noble gases are gases at room temperature. That's why I call them gases. But 4.2, 27, 87, 120, 165 Kelvin. The boiling point is going up. And we talked about boiling, right? In order for something to boil, the particles have to get enough energy to break loose from those forces of attraction. We talked about evaporation and playing Red Rover, right? You're playing Red Rover. If the Red Rover line is weak, if the intermolecular forces are weak, it's easier to break through. It's easier to evaporate. It will boil at a lower temperature because the temperature is related to the speed of the runners in the Red Rover game. If they're running fast, if they have to run fast to break through, that's a higher temperature. So there's this correlation between strength of the dispersion force. Helium has a weak dispersion force. It boils at a very low temperature. That's 4.2 degrees above absolute zero. You really have to work to get helium to be a liquid. Xenon has stronger dispersion forces. It boils at a higher temperature, 165 Kelvin. I think the best way to remember this is to be able to think about it and reason it out. You know, think about playing Red Rover, and the people's grip is the strength of the intermolecular force. If the intermolecular forces are strong, the people running at it have to be going faster to break loose. People running faster is higher temperature. If the forces are strong, it will boil at a higher temperature. Weak forces boils at a lower temperature. So we should be able to answer questions like this. Which hydrocarbon has the higher boiling point? So these are two molecules, but they are similar because they both contain only carbon and hydrogen. So which one of these is bigger? This one's bigger, right? You could calculate the molar mass, or you can just think about it. Well, this one's got 2 carbons and 6 hydrogens. That's 1 carbon and 4 hydrogens. This has to be larger. Larger molecules are more easily polarized. So when you push the electrons around, it happens more frequently, and the magnitude of that partial charge is going to be larger. So higher polarizability, stronger intermolecular forces. So which one has the higher boiling point? The larger one, the one with the stronger intermolecular forces. The next force is called the dipole-dipole force. And this exists in all polar molecules. We talked about how to determine if something's polar a while ago. Polar molecules have permanent dipoles. The dispersion force was between these spontaneous dipoles that come and go, right? Polar molecules are always have dipoles. So they always have a positive and negative. And so that electrostatic attraction between those dipoles is always present. So it makes sense that this is a stronger force of attraction. So just to reiterate, all molecules have dispersion forces. Polar molecules also have dipole-dipole forces. So we expect polar molecules to have higher melting and boiling points than nonpolar molecules of a similar molar mass. This is formaldehyde. If we look at the Lewis structure for formaldehyde, we can predict that it's polar. It doesn't have any lone pairs on its central atom, but it's got 2 hydrogens and 1 oxygen. This one is different. The 3 things bonded to it are not the same. And so we would predict from my little tricky rules that this would be a polar molecule, and it is. The oxygen is more electronegative, and so this end of the molecule has a negative charge and this end has a positive charge. So when 2 formaldehyde molecules are near each other, there's an attraction between them, and that's the dipole-dipole force. It's a force between a dipole in one and a dipole in the other. That's why I like induced dipoles for that first force, because I think it's a lot more description. I really don't know where they got dispersion forces from. I should look that up. I'll do that in my free time later. Yeah, maybe in 15 years or so. So here's formaldehyde, which we just looked at, and here's ethane. Anytime you have a hydrocarbon, just carbons and hydrogens, that's going to be a nonpolar molecule. We look at these molar masses. They are almost identical. Here are the structures. When we look at these, when we look at the ethane molecule, we see that it's very symmetrical. It's nonpolar. Look at these boiling points. Minus 19.5, minus 88. This is a lot lower. Ethane boils at a lower temperature because it's a nonpolar molecule. The only force that's holding it together is that weak dispersion force. Formaldehyde is a polar molecule. It has stronger forces holding it together. We see the same trend with the melting point as with the boiling point. Any questions? Polarity also affects miscibility. I think I told you about this word a long time ago in lab. Miscibility, you can think mixability. Miscibility describes the abilities of two liquids to mix together without separating into phases. We know that oil and water don't mix. You can shake them up, but they separate into layers. But things like alcohol and water do mix. They'll mix up very nicely together. So in general, polar liquids will mix with other polar liquids. But polar and nonpolar do not mix together. And so we talk about like dissolves like. If the two things are similar, they will mix together. If they are dissimilar, they will not. So, oily hands, oily clothes, plain water is not going to wash that away because the oil just will not mix with the water. Oh, pictures. Yeah. The salad dressing is making me hungry. So all polar molecules have dipole-dipole forces. We need to be able to recognize polar molecules. So there's the Book's method, and this is my method, which is going to work most of the time. We talked about this before, but a molecule is nonpolar if both conditions are true. No lone pairs on the central atom, and the atoms bonded to the central atom are identical or have the same electronegativity. So determine whether each molecule is going to have dipole-dipole forces. So what we're really asking is, are these molecules polar or nonpolar? So Ci4, and I wrote the name out because it kind of looks like chlorine 4, but it's carbon tetraiodide. So that's going to be carbon with 4 iodine atoms attached to it. And if you go through and do all the dots and everything, ooh, that's a really big dot. There's size. It's better. No, it's kind of small. Oh well. Each of these is going to have lone pairs. But there's no lone pairs on the central atom, and it's all iodines. Polar or nonpolar? Nonpolar. So does it have dipole-dipole forces? No. So this guy's a no. How about CH3Cl? Yeah, that does. And you can draw that out if you need to. There's CHCl. How about HCl? That's going to be polar. There is only one bond in HCl, right? Because there's only 2 atoms. The 2 atoms are different. It's got to be polar. Any questions? The last type of intermolecular force we're going to talk about is hydrogen bonding. Really what these are dipole-dipole forces to the extreme. They're just extreme dipole-dipole forces. A super dipole-dipole force. So this happens when we have polar molecules that have hydrogen atoms bonded directly to fluorine, oxygen, or nitrogen. That's not what I wanted to do. You seen the movie E.T.? What did E.T. say? He pointed to the sky. Phone home! E.T. phone home! Right? Phone home. Fluorine, oxygen, or nitrogen bonded to hydrogen. That's what you have to have hydrogen bonding. So all you have to do is think about ET. Why? Well, these atoms, fluorine, oxygen, and nitrogen, are the three most electronegative elements. So when they bond with hydrogen, they really hog those electrons, and these bonds are more polar than regular polar bonds, because the degree of polarity depends on the difference in electronegativity. So this is a high difference of electronegativity, and these are small atoms. And so this allows neighboring molecules to get really close. These forces of electrostatic attraction depend very strongly on distance. And so if the molecules can't get real close to each other, the forces are going to be weak or non-existent. That's why gas particles act like they have no neighbors. They're too far away from each other to have these forces of interaction pull them together. In a solid or a liquid where things are touchingly close, they become important. So here we have hydrogen fluoride. Fluorine hogs the electrons, and so this is a large partial negative charge and a large partial positive charge. The negative end of one hydrogen fluoride molecule is strongly attracted to the positive end of the neighboring one. And it's the same idea as the dipole-dipole forces, it's just extra strong. So polar molecule, ET phone home. Methanol. Here we've got methanol. Methanol has an oxygen-hydrogen bond, and it's a polar molecule, so ethanol has hydrogen bonding. The positive end of this one is attracted to the negative end of that one. If we compare methanol and ethane, so this is a hydrocarbon. We look at the structure of this, and it's all nice and symmetrical. There's no fluorine, oxygen, or nitrogen. And here's methanol. And here we have an oxygen-hydrogen bond. Phone home, fluorine, oxygen, or nitrogen bonded to hydrogen. The molar masses are similar, so any differences we see aren't going to be due to the dispersion forces. Look at the boiling points. This boils at 64. This boils at minus 88. The difference between these is this one only has dispersion forces. This one has dipole-dipole forces and hydrogen bonding. We also see a big difference in melting point. Questions? See puzzled looks, but no verbalized questions. Maybe they'll come later. Water does hydrogen bonding. Water is a polar molecule and has a hydrogen-oxygen bond. So we get this force of attraction between the positive and negative ends. What we see for water is a lot of unusual behavior. Water actually boils at a remarkably high temperature. Oh, I don't have a graph. I need to put a graph in here. Water boils at a remarkably high temperature given its low molar mass. It's only 18 grams per mole, and yet it boils at 100 degrees Celsius. We go back and look at these guys. These have higher masses, but this even methanol boils at 64. Hydrogen bonding is really important. It plays a big role in biological processes. You've probably heard of DNA, right? DNA is the genetic code that your body uses to reproduce. And DNA is a double helix composed of two strands. And those two strands are held together by hydrogen bonds. And what happens when the DNA reproduces is those hydrogen bonds get broken, and then new hydrogen bonds form, and there's a specific way it does it between the bases. I'm not going to get into the details, but it's really, really cool. It's all hydrogen bonds.
This is so that it's low energy for transcription and translation, because they're weaker than covalent.
Yeah, because it's almost like magnetic, and so, why do we use magnets instead of glue?
Right.
Because you can open the door and close it again, and open it and close it, and so you can unzip the DNA and bring these other pieces in, and they're going to fit just right, and then you can hook them together and make a new strand, and it just snaps together again. It's really, really cool. So this is an overview of types of intermolecular forces. Okay, which has the higher boiling point, HF or HCl? HF. Why? They're both polar, right?
But it's stronger electronegative.
This has hydrogen bonding because it's a hydrogen fluorine bond. And so the HF will have a higher boiling point because it has hydrogen bonding. HCl does not. Dang, I was hoping we'd finish.